So today is lecture number 4. Okay, just to clarify, we talked about diodes, but diodes are not part of this course. Okay, we studied this so that you can connect the course. Generally, in every IIT or every place, the course of analog circuit designing start with the diode, but we don't have much lecture, so I'm using our laboratory sessions also. Right? But those circuits which we have discussed are commonly used in all the places. If you are in power electronics specifically, they don't use BJT, they use diodes or capacitors. The last time which we have studied was charge pump. It's known as Dixon charge pump. And this is the one which is used in most of the circuits. But note that input has to be sine wave. Input has to be sine wave. Okay. Otherwise it will not amplify. Anyway, so other than that, we have studied following things. So we studied the BJT and MOSFET structure, right? We know that how they look like. We also know the IV characteristic. We also found out, or we understood what is small oblique large signal, and we also know the equivalent model, but that model was small signal, by the way. So we also know small signal model of BJT. Unfortunately, the derivation is not given in any book, but we derived it using two-port Y parameters. Some old books you'll find they have derived with H parameter. They don't use Y parameter, but they use H parameter. So you can also derive two-port H parameter. You can derive Z parameter, ABCD parameter. Any of the parameter you can follow. But for our course and the book which we are following, Behzad Razali, he is using Y parameter. That's why we are going to use Y parameter. But if you are taking any book which is before 2000, all books are using H parameter. But generally, that is little bit complicated sometimes. So Y parameters are easier ones. So you will realize today that why it is easier. Anyway, so is there any doubt till now in these topics? If you have doubt, we can revisit that, or if you have doubt on diode, we can talk maybe in laboratory or maybe offline. Right? No doubt that we can move ahead. Okay. So you must have studied. Okay, should have. You have studied this kind of characteristic, right? But this is not the correct one. Do you know the correct one? The line is will have some slope. This particular effect is known as early effect. You studied early effect. Okay, very nice. So if you have studied this early effect, let's forget about early effect then. We'll talk about something else, which is for MOSFET. In MOSFET, this also looks like this one. This is known as VDS set line, and this is actually equal to VGS minus VTH. For varying gate to source voltage and threshold voltage is constant, this line will be there. And this is happening because of one reason. You want to make MOSFET like this, but MOSFET has some overlap. see here, there is some overlap over here. You wanted to make the channel length of, like, you wanted to make the channel length like this L, which you are like aware of, but effectively the channel length is this much only, and it's reduced by this delta L. And because of that, earlier in the equation of drain current, it was like I'm writing only in saturation, because this effect is only valid in saturation mode of operation. In the case of BJT, it's only valid in active mode of operation, because the names are swapped. And in this case, the equation looks like this one, where there is no control from drain to source. In this equation, there is no drain to source voltage, right? And that's why our some of the parameters in like y12 and y2 y22 becomes 0, because this was del IB by del VCE, and this was del IC by del VCE. Sorry, in this case it will be in the case of MOSFET, when we are going to do this, the equation does not have any VDS, like the case of BJT, where in the equation of collector current there is no VCE. There is, other things are available, VBE is there, uh, but VCE is not there. So these things were going to 0, right? Those were 0. But in reality, when there is such kind of effect, which is known as channel length modulation. So the way you were calling the earlier effect was early effect voltage. Do you know why it's called early effect voltage? This early is not English word early. This is the name of the scientist who invented it. Okay, for those people who do not know, this is the name of the scientist who did it. That's why it's E is always in capital. Remember this. This is the name of the scientist. It was invented by him or observed by him. That's why it's early effect voltage, and that's the name. Okay, this is the case for BJT. And for MOSFET, it's known as channel length modulation, because channel length is actually decreased by some factor, or some cases it increases also, and the equation is changed by 1 plus lambda VDS, where VDS is drain to source voltage and this lambda is L by delta L. So that's the ratio of channel length, right? So the equation has changed, and similarly, uh, when we are going to have, let's talk about early effect first. So in the case of early effect, if I draw right, so when we are extending this, it will meet only at one point. That was the early effect in reality, that it's going to meet here at the voltage called VA, and that is the potential which will be included in your equation. And similarly, same thing is happening for the case of channel length modulation. Where this becomes ID with respect to VDS. And this is VGS. So as VGS is increasing, this is like this. But note that this line does not look like this. It looks like this one. So this is called VDS set line, and this is in saturation mode, and this is in linear or triode mode. So if you remember the small signal equivalent model of BJT. So now onwards, if I am telling this word small signal model of BJT, just draw that model in your brain like this. Remember this if you are in analog circuit design, you have to remember this forever. You cannot forget that, right? So this is base, emitter, and collector. But in the case of MOSFET, the good part of MOSFET is its input impedance is infinite because it's not allowing to go any current inside, and it's a voltage control. If you want to derive this, you can derive it, right, using Y parameter where gate current is 0 and ID is equal to mu n C ox by 2 W by L VGS minus VGS square. So del ID by del VGS is going to give you GM, and rest of the terms are not present in MOSFET. So it's del ID by del VGS, right? So these are the two different things in BJT and MOSFET. BJT has this small signal equivalent Y parameter model. If it is H parameter, it's different. If it is Z parameter, it's different, right? You have to derive it separately. But most of the engineers in this particular era, they are following only and only Y parameter. All the new engineers. If you talk with some old professor, he is going to talk about H parameter only. So it's up to like it's a convention. At the end, you will have the same answer. Right? And we are following because of only one reason. It's Behzad Razavi book which I am following. Right? So that is also the one thing. Okay. So can you like remember this both the things forever, right? Then like you are not supposed to draw it again and again. You have to just remember it that inside input side R pi, this side VB GM, other side it's like there is no impedance at the input. Just you have to remember this current mirror. But when we are adding this early effect or the channel length modulation, what is happening in the collector current equation? VCE is also playing the role, right? VCE is also there, or in the case of ID current, VDS is also there. And if you find out del ID with respect to del VDS, you are going to have one more extra term. You can add that one here, and let's call it RO. This is because of early effect, and it's known as early effect resistance. Or you can add here one more resistance and name it as RO and call it channel length modulation resistance. Whose value is del ID by del VDS when this is in saturation mode. This equation has to be in saturation, right? So then you can have this thing. So now one more element has been increased. Can you remember this? Now this is the thing, right? Other things will be added afterwards, but right now for a time being, this is the case. Okay, so let's understand one thing. How much you are good at R0. So this is base, emitter and collector. So what we are doing right now, this must be available on the first page of the book before starting any chapters, before starting any content, preface, anything. This is written. I'll tell you that what is that. So if you are like, can you now you can see this, right? Forget about this, and this is what written. If I am looking into this base, what is the impedance? R pi. If I am looking into emitter, what is the impedance? Hmm? You have to remember the R0 also is there. Hmm? What is that? R0. But remember that among these three, 1 by Gm is the lowest one, other two, like this is in something in ohms, 100 ohms or 200 ohms, and these two are in kilo ohms, right? Or you can say this might be like something like 500 ohms, if this is 100 ohms, and this is in some 10 to 20 kilo ohms. This is the biggest one. So, can we approximate this to 1 by Gm? Right? And if I am looking from here, what I am going to see? Hmm? Not infinity. R0. Now R0. Right? So this is what I was talking about. The first page, right? If you are looking at the first one, like first row only, right? So if you're looking into base, it's R pi, and this is the thing you have to remember. If you cannot remember, you have to just remember the small signal model, and in your brain you have to do the Thevenin theorem, right? So, and this might be the like mostly all the interview questions people are asking such kind of questions. What is the impedance looking into base, collector, and afterwards the circuit will become bigger and bigger. We'll add more transistors. That's why it's on first page, right? That's why it's on first page. Okay, right? So now there is no problem, right? You know that at the base side it's R pi, at emitter it's 1 by Gm, and collector R0. You also know that the smallest quantity is 1 by Gm, right? And R pi is second second smallest quantity, and thereafter R0. You can keep it like this, right? So this is just for an approximation. We are going to use this. Okay. Okay. Now I'm not drawing the small signal model for MOSFET, but you have to draw in your mind, or if you want, you can use your notebook and tell me what is the impedance I'm looking into gate. Okay, for those who forgot, let's. But afterwards, I'm not going to draw this one because this will stay for many, like almost for next 20 lectures. I'm going to talk about these impedances, right? So it's infinity because there is no current is going inside. It's infinite. It's shown here. Now tell me if I am looking into source. What is the impedance if I am looking into source? 1 by GM. Let's make 1 by GM in shunt with RO. However, I can approximate this to 1 by GM. The reason is 1 by GM is smaller than, much smaller than R0, right? So this is, what about this one? R not, right? Is there anybody who has problem in understanding this one? Because in the book, the next page is talking about a MOSFET. Okay, before starting anything, like it's you should know these things. Okay, if there is no problem, let's again revisit the biasing techniques which we talked. Like this is just for the information, you remember or not. So if you remember, we agreed to use this kind of structure. So I'll ask you the following questions and you have to answer me. Okay, so why we have chosen this configuration? By the way, what is the name of this configuration? Yeah, so it's common emitter, but it's emitter degeneration. But I like to use MOSFET because it has certain advantage. If I change this one like this, what will be the name of this configuration? Source degeneration, right? Because we have degenerated source. Okay. Why you have used R1 and R2 like this? What was the reason to have R1 and R2? Ratio is maintained and like it's not varying with respect to three. Actually, our main agenda is our circuit has to be PVT independent. Do you remember this? So what is PVT? Is process, voltage and temperature, right? So any process or any voltage. So this transistor is made up of TI, Fairchild or analog devices or anything. In all the cases, it should work. That's called process, whose beta is, even if it is varying, it has to be same. Voltage, if your VCC or VDD in the case of MOSFET, if it is varying, it should give the same gain as we want, and temperature also. So we want uniform output for across process, voltage, and temperature. That's why we are designing this, and it has to be robust again against all the PVD. Right? Okay, what is the role of adding RE by the way? Degenerating, that's the name of the resistance. So why we are adding this? If we don't add that, what is going to happen? If we don't add this, that was a technique number 2. Technique number 3 was adding the resistance. We want to have the linear relation. I don't want anything which is non-linear. So this ID current, I want the linear relation with respect to other voltage parameters. So that's why I have added this one, right? So any doubt in this one? Like, and other than that, why we adding this capacitor? What is the role of this capacitor? Hmm? It's a coupling capacitor, but why we are adding this capacitor? Yeah, so at the source side, there is a 50 ohm resistance. So what? So what is going to happen in that case? So the current coming from this one is flowing from here also, right? So we are not blocking the current which is going from the input side, but we are blocking the current which is coming from VCC or VDD side, right? We want this voltage as R2 by R1 plus R2 times, in this case, VDD, right? That's why we are doing this. Okay, so this is biasing scheme, and this is the mostly used common emitter amplifier. And this was biasing means it was DC operating point or the quiescent point, or also called known as Q point or biasing. All these things are synonyms, or you can say that it's a common mode. Right? Any of the what you are seeing means you are fixing the DC potential for this transistor, and you are fixing that this transistor will be in saturation mode of operation or maybe in other mode of operation, whichever you want. So in this case, when you want to have the amplification, you want to have it in saturation, right? So we did this one. Now, what is next part? The next part is we want to amplify. So we want to amplify not at DC. We don't want to get the amplification at DC. We want something at frequency, right? And gain, and that's why like we are going to call it AC gain or the small signal gain. Small signal AC gain. So when we are doing this small signal analysis, so earlier we were doing the DC analysis, common mode analysis or the Q point analysis. The next one is small signal analysis. When we are doing the small signal analysis, we have to understand that it's an AC analysis, means it's in the presence of only sine wave kind of thing, and all common mode voltages or bias voltages or all DC voltages will go to 0, right? Let's agree on this. There is no problem, right? So in that case, we are going to add transistors, like some other circuits afterwards. So here there is one transistor whose name is M1. By the way, this transistor has been copied from Beza as a blue colored book, but similar thing is also available in red colored book, microelectronics fundamentals. So it's not much difficult. But so what I'm saying here, one thing is that unlike BJT, so BJT has one thing, that there is one current IB, there is one current called IC, and there is current called IE. And we learn that IB, IC is equal to IB plus IE, because that's the Kirchhoff's law. And we have approximated this one to this, IC equal to IE. But that's not the truth. IB will be always there because of the reason there is R pi. However, in the case of MOSFET, gate current is 0 because input impedance is 0, and drain current is equal to the source current, right? This is possible because this is voltage controlled source. We'll talk about like why it's, this is current controlled current source, but in this case, what is going to happen, we'll talk later. Whether it's voltage control voltage source or voltage control current source, but its input side it's voltage, right? So I'm saying that, so this is the technique, by the way, to find out the gain and other things. So this technique says that we don't care about what is the impedance inside, because this impedance is infinite also, not is. This is always infinite. So the input impedance is MOSFET is infinite, However, I am going to define other things just to find out gain. If I want to find out gain for this circuit, assuming the fact that input has enough DC potential, this capital letter V in are denoting that's a DC quantity, this one is AC quantity, right? And this is sufficient enough to make this transistor in saturation. So then, if I want to find out the gain, I need to find out the current flowing through this one. Or you can say that, can we write out V out? What will be the V out? VDD minus IDRD, right? That's okay, right? So just you are following the KVL, right? So VDD, because it's like this. So VDD minus IDRD, that's equal to V out. Now, it's the same current which is flowing from here, by the way. And in saturation, this ID is equal to mu n Cox by 2 W by L VGS minus VT whole square times RD. Are you following it now or any difficulty? Okay. So this is the equation. Now I want to find out the small signal gain. Small signal gain is always like del V out with respect to del V in, because I don't want any DC quantity. So this DC quantity will go to 0, and this one will become. Can you solve for me and tell me what will be the value? If I take the partial derivative of V out with respect to V in, note that V in is nothing but VGS. V in is nothing but VGS. Okay, W by L. So minus will be there, right?
VGS minus VGS.
VGS minus VGH into RT. But what about these constant values? Mu and Cox by 2 time, huh?
2 will be cancelled by it.
Yeah, so 2 will be cancelled. Yeah. So this is same as del ID by del VGS. If you remember, if you do this one, del ID with respect to del VGS, which is equal to GM, that is also equal to same thing. Mu and Cox where VGS minus VGS. Right? It's also same. Del ID with respect to del VGS. So in Y parameter, this is Y21. In our this GM is nothing but del ID by del VGS, which is Y21. Right? So I can replace this quantity here and call it as minus GMRT, right? But this was the classical way to find out the gain. But if you want to find out from impedance property, what you are going to see that the current flowing through this one and the current flowing through this one are same. Means it's depending on the ratio of these resistances, and that is going to give me the gain. So in that case, what I am going to do, I am going to look at the output side. So if this is output, okay, let's assume that this is some device and this is source side, this is drain side, and other circuit is also connected. Other circuit is also connected. It might be resistance, it might be much more bigger than just one resistance. So in that case, if this is output, at output you need to see the impedance. which is actually nothing but ZT. Similarly, see the impedance at source side, because the current is flowing from here to here, sorry, from here to here, and both the currents are same. So if I know what is the resistances in the path of drain and in the path of source, I can find out the gain. However, remember the input impedance of this device is still infinity. This is a technique where I am redefining the input port with the source. Right? So this is a technique for which, so what we have solved just now, this one is the classical way, you can derive the gain. But let's assume that I have this circuit and I want to find out the small signal AC gain. I'm going to follow only one thing. I'm going to see what is the impedance at the output side. So at this point, output impedance, and from here, what is the source impedance? So this output impedance divided by source impedance times the current which is flowing through this one, which is ID, and the current flowing through IS. Both are same, so it's gone, right? So this ratio is going to give me the small signal AC gain. So now let's assume that you want to find out that. Do you know what is the source impedance? What is the source impedance? Looking into source. 1 by G. What is the source drain impedance? Only drain in the, it's not infinite. RO, right? So here, let's draw the small signal model. So for those people who are not able to follow exactly. And when we are doing this, this is for, here I am applying V in, here I want to see V out, and what about this RD? RD is connected with VDD, right? But we agree on one thing, that we are doing the AC analysis. In AC analysis, all DC potential will go to zero. All common mode voltage, all DC potential will go to zero, because we are doing only AC analysis, and at the time we are going to apply only AC signals. So this VDD is going to be connected to zero, but this is known as AC ground. It's not all-time ground, it's AC ground, right? And this is going to happen, right? Now, tell me, what is the impedance looking from here? You already found out 1 by GM, right? You already knew that it's 1 by GM. What is the impedance looking from here? Which is here. RD in shunt with RO. So this will become GM times RD in shunt with RO. But notably, when we are looking into this impedances, it's in the opposite direction of the drain current. Look at this. It's an opposite direction of the drain current flowing through this one. So if I'm looking from here, if I'm applying the Thevenin here, and if I found out equivalent Thevenin resistance inside this one, actually I am applying current in this direction. However, the drain current is coming in opposite direction. So the value has to be incorporated over here, and it has to be minus GM. If this current is flowing upside, then it's plus, but it's going in opposite direction, that's why it has to be 1 by GM, but with the minus sign. So the gain becomes minus GM times RD shunt with RO. When you have considered the channel of modulation, unfortunately, I forgot that I made mistake while solving. While solving this one, we have not added the channel and modulation resistance. Right? In this equation, we need to have the 1 plus lambda VDS. Then RDS is also RO is also available. By the way, there are few more names of channel and modulation resistance. So some books are writing R0, some books are writing RDS. Both are same, by the way. Okay, some books are following RO, some books are following RDS. Behzad Razavi is following R0. Okay. So any problem in this one? This circuit, how to solve this one? Yes or no? Let's try a few more. Okay, so if this is the transistor, I need to find out the impedance looking into source. What I am going to see in this transistor, if I am looking from source, what I am going to see as impedance? 1 by G. What is the impedance I am looking into this one and this node? R, right? Yeah. So what is the gain of single transistor? Single transistor without any load. Minus Gm times Ro, right? So if it is gain of single transistor, we are going to call this one as intrinsic gain. The name of this gain is intrinsic gain, right? Because it's gain of one single transistor. So if somebody is asking you what is the gain of the single transistor, it's GMR, right? And that's also true for the case of BJT. That's also GMR and having minus GMR, by the way, right? You can change the model and answer will be same, right? Because here it's R pi and R pi is not winning over GM, so you can approximate it this quantity R pi in shunt with GM with R0 as 1 by GM, right? Because R pi is much bigger than 1 by GM, so it's not coming into picture. So same gain is coming, right? Now let's assume that I am making one transistor like this, and I want to find out the impedances at all the nodes, gate, drain, or source. So what I am going to see at gate, if I am fast, please let me know because this is very important things. Are you following, right? Okay. So what is the gate impedance? Why RO? Hmm? You look at that one more time, please. Yeah, so RO in shunt with 1 by GM. Very nice. So you can approximate this to 1 by GM. And there is no doubt that at drain side also I am going to see the same thing, right? It's shorted, so it's same. What about the source impedance? What is the source impedance? The good part of transistors is if you are looking from source, it's always 1 by GM, right? Because there are three transistors, three different components are in shunt. One is infinity, one is 1 by GM, and one is RO. So RO and infinity are gone because 1 by GM is much more smaller than other two quantities. So it's 1 by GM, right? And this is also the case for BJT. If you want to solve, you can solve that. Right? If you're looking into this one, it's R pi in shunt with 1 by GM in shunt with RO, whereas 1 by GM is the smallest one, so I can approximate that one to 1 by GM. And same for this side, same for this side. So everywhere it's 1 by GM. Right? So this is one thing. And such kind of so here generally we have two junctions. If you are shorting this one, this is almost gone, right? So if you want to implement a diode using MOSFET or BJT, you can short gate and drain, or you can short base and collector. Yeah, or you can go other way around also if you wish to make a diode. So this kind of configuration is known as diode configuration. So now, what if I'm making this kind of circuit? One more time, I'm just solving for you people without drawing the any small signal model. So this is V in, this is V out, and this is M1, and this is RD. So I know looking into this one is going to give me how much? 1 by Gm. Very nice. But here at the output side, there are two branches, one like this and one like this, and this is also ground. So both are in, if there are two branches, they are in parallel. So I have to see what is in this direction. What is in this direction? At the drain side, what I am going to see are not. And if I am looking upside with respect to ground, what I am going to see? RD. So in total, this is RD in shunt with RO, and for this one, gain is nothing but minus GM times RD in shunt with RO, right? Yes or no? Let's do something else over here. Look at this. This is, it's a diode connected configuration, by the way. So what I'm going to see, and it's a PMOS. Okay. So what I'm going to see now? Tell me. From source side, it's 1 by Gm. What this side, it's again R not. If I'm looking up, what I'm going to see? 1 by Gm, because any diode connected configuration, any side you are seeing, either from gate, drain or source, it's always 1 by Gm. But let's call this one as 1 by Gm2, and let's call, so this is already 1 by Gm1. So now can you tell me the gain? Minus Gm1. Okay, are not in shunt with 1 by Gm2, right? However, 1 by Gm2 is winning here. So it's, this, I made it something wrong. Okay, minus Gm2 divided by Gm1, right? No, this one was correct, right? So it's a ratio of two things, minus Gm1 divided by Gm2, right? So look, both the ratios are very small, right? This is also in ohms and this is also in ohms. So if you are making such kind of circuit, your gain will be very poor, right? In such configuration. Now let's talk something different thing. Let's assume that I am connecting this gate to some potential called 1 volt. Okay. So now can you tell me what is the impedance looking from here and the impedance looking from here? I know that gate impedance is always infinity. What is source? 1 by Gm. While doing this analysis, what we are doing, we have to note that this is ground, by the way. Okay, this is the difference. If you have to draw the small signal model and you have to do that, this 1 volt has been transformed to 0 volt because it's small signal AC analysis where DC goes to 0. By the way, this is AC ground. Yeah. Yeah, Suraj. Okay. So any doubt till now? So please remember the small signal model. We'll do much more things than what we have done till now. The entire course is all about input impedance and output impedance. Okay. So if you are expert of Thevenin and what we have drawn, then there is no problem. Right?